Let's jump right in. Welcome to This Explainer. Today, we are unpacking a genuinely fascinating new paper fresh off of arXiv that is tackling an absolutely massive problem in meteorology. We're talking about how to accurately reconstruct four-dimensional cloud fields using just a handful of ground sensors. The AI framework is called AtmoFuseNet, and I promise you the way this system pieces together the sky is nothing short of incredible.
Here's our quick roadmap for today. We'll start with the atmospheric data problem, introduce AtmoFuseNet, break down its 3 stages of fusion, look at some real-world benchmarks and limitations, and finally touch on how to actually build with it.
Section 1. The atmospheric data problem, the challenge of heterogeneous sensors.
So we first have to establish the core physical challenge here. Clouds are massive, 3-dimensional, and highly dynamic. But our ground-based instruments, they capture a really narrow, fatally mismatched slice of that reality. Sky cameras give us beautiful, high-resolution 2D textures, but absolutely zero depth. Meanwhile, millimeter-wave radar punches right through the clouds to give us reflectivity and vertical velocity, but its horizontal resolution is terrible. Add ceilometers to the mix, which track aerosol heights beautifully but give us almost no volumetric detail, and you are left with a very messy, fragmented picture of the sky.
Now you might be thinking, why not just combine all this data at the end? Well, traditional data merging is kind of like trying to blend fully baked pies together. The information loss has already occurred because the spatial scales differ so drastically and the physical relationships between optical reflectance and radar backscatter are super nonlinear. Simple late-stage concatenation just completely fails. You can't just stack this data, you literally have to weave it together from the ground up. That brings us to Section 2. Introducing AtmoFuseNet, bridging 2D texture and 3D space.
So instead of that flawed lead-stage merging, AtmoFuseNet uses something called cross-modal fusion. It treats the merging of these different sensor streams as a hierarchical alignment task. By processing the features layer by layer, it actively grounds those flat 2D camera textures into actual 3D space across multiple levels of abstraction. This is a real game changer because it prevents the massive information loss that usually happens when you try to project 3D volumes onto 2D planes.
Moving right along to Section 3. 3 stages of fusion, the pipeline deep dive.
Let's actually trace the exact journey a data point takes through this architecture. It moves through 3 distinct phases: raw feature extraction in stage 1, physical constraint refinement in stage 2, and finally kinematic estimation in stage 3.
Okay, in this first stage, the Cross-Modal Hierarchical aggregation module does the heavy lifting. This is where the network extracts pyramidal features from the camera stream and essentially learns to attend to radar-derived height constraints using layer-wise cross-attention. It's figuring out exactly how to map the visual texture right onto the physical radar profile. Then we hit Stage 2, Conditional Variational Refinement. Here, the module applies differentiable forward models to that fused volume. What's happening is it's forcing the AI's output to satisfy actual physical consistency constraints, rather than just blindly guessing based on data patterns. This gives us a much-needed probabilistic framework to fill in those massive volumetric gaps left by our sparse ground observations. Finally, Stage 3. A correlation-based motion estimator recovers per voxel 3D wind vectors simply by tracking how the volume changes across consecutive time steps. This is honestly brilliant because it entirely avoids the need for direct Doppler wind measurements. As anyone in atmospheric sensing knows, those are often incredibly noisy or just completely unavailable in standard ground setups. Let's look at Section 4, Benchmarks and Limitations, Testing in a Semi-Arid Site. To see how this holds up in the real world, researchers tested AtmoFuseNet in a really harsh semi-arid environment featuring low humidity, high aerosol loading, and rapid cloud cycles. The result? A mean absolute error of just 0.026 grams per cubic meter for liquid water content. It handled sparse, noisy data exceptionally well and completely crushed traditional retrieval baselines. And right alongside that accuracy, the framework achieved highly impressive 1.18 meters per second mean absolute error for wind speed. And remember, it calculated this without relying on direct Doppler wind measurements at all.
But we do need to impartially note the specific limitations outlined in the paper. The variational loss requires really careful tuning, so physical constraints don't accidentally overpower the actual data signal. Also, the motion estimator assumes quasi-steady flow, meaning it might struggle or break down during very rapid, violent convective events. And lastly, running those differentiable forward models absolutely adds significant computational overhead.
Let's wrap up with Section 5, Building with AtmoFuseNet, the Developer Playbook.
If you are working on atmospheric modeling or your own sensor fusion projects, here is a clear blueprint to follow. First off, you absolutely must account for sensor drift. Perfectly align your camera intrinsics, radar coordinates, and ceilometer bore sight. Always verify your cross-modal weights using synthetic data before touching the real stuff. You'll need simulation libraries to integrate custom forward models. And a quick pro tip, always track your liquid water and wind metrics separately since they diverge fast when cloud morphology changes. And for sure, cache your intermediate volumetric states to save your compute power.
If you want to dive into the code yourself, you can grab all the implementation details, the training scripts, and that exact semi-arid valuation dataset directly from the computer vision and AI section on arXiv. Just look up identifier 2606.30647.
So as we close out this explainer, I want to leave you with this provocative thought. If we can achieve this level of dense, volumetric reconstruction from just a few scattered ground sensors, how drastically will this reshape our global climate models and weather forecasting in the next few years? Thank you so much for joining me today. Keep exploring, and I highly encourage you to go read the source paper for yourself